So to go over oxidation and reduction a little bit more, I'm actually going to go through part 2 of the group activity from this week. Based on talking to students during class and looking over the worksheets, this seems to be where students were having the most struggles. I will post a copy of the completed worksheet on Blackboard as well, but I wanted to kind of talk through some of the ideas that were in that part of the activity. And so the first thing I want to look at is the definitions. And so we were given a couple of different definitions of oxidation and reduction. Now, for all oxidation processes, we always see a loss of electrons. For all reduction processes, we always see a gain of electrons. Now, sometimes it's hard to see that we're gaining or losing electrons. It's much easier for some of our organic or biochemical reactions to look for the addition of oxygen, loss of hydrogen, loss of oxygen, or gain of hydrogen. These are easier things to see for some reactions, but ultimately, somewhere along the way, this loss or gain of electrons is still happening. It's just not as easy for those biochemical and biological reactions. So any of these definitions will apply. Now, one thing we note about oxidation and reduction reactions is that that always happens as a pair. If I have an oxidation, somebody must be undergoing reduction. So I have to have both an oxidation and a reduction. I can never have two oxidations. I can never have two reductions. I must have one of each. And if I have one, I must have the other. So when we look at ionic compounds, for example, we talked about cations formed by the loss of electrons and anions formed by the gain of electrons. And what we saw is that the cations had to lose the same number of electrons as what were gained by the anions. And so we see that there has to be that equality in those two values. And so as a result, what we want to look at when we're going to start out first is look at a basic formation of an ionic compound, and we'll look at how we identify the oxidation numbers or the charges on those for both the atoms or the elements in the reactants and that product of the iron oxide. So we did talk about ionic compounds a couple of chapters ago, so you might need to go back and review that just a little bit. And what we want to look at is we want to determine the charge on these substances. When I look at iron, notice there's nothing written there that gives it a charge. It just says it's a solid. It doesn't show a charge and it's not in a compound. Therefore, it has no charge. This is neutral. I see the same thing for oxygen. Again, it shows the element, and it doesn't show a charge with it. It doesn't show a plus or minus or anywhere. So therefore, they both must be neutral, which means they have a charge of 0 on them. So we're starting both at a charge of 0. Now, I want to look at the iron oxide, and I'm actually going to go down here to the bottom so I can expand upon this a little bit, have more room to write. When I look at my Fe2O3, I don't know what the charge is on iron because iron is a transition metal, therefore it has multiple possible charges. But I do know that the charge on oxygen must be a -2 charge. When I look at my periodic table, what I see is that oxygen is 2 away from looking like neon, from having the same number of electrons in that outer shell as neon, so it's going to gain 2 electrons. Now, when I look at this, I don't know what the charge is on iron, so I'm going to actually call that X for right now, and I know the charge on oxygen is -2. So I'm actually going to show you how we calculated this just as a refresher, and I know that 2 times X, because that's the charge on iron, okay, plus 3 times a -2, because I have 3 oxygens and they each have a -2 charge, must equal 0, because overall this is a neutral molecule. There's no charge written up here, therefore it is neutral. So I know this expression, this mathematical expression, must be true. So what I'm looking at here is I have a -6 from all of my oxygens, and I have 2X here from the iron. So I end up with 2X equals 6, so X equals 3. So I see that the charge on my iron ions is a 3+ charge. So that lets me see that iron goes from a 0, up here we had iron as a 0, a neutral element, to iron with a 3+ charge. Notice that the subscript helps us figure out how many irons were in the molecule, but they don't actually tell us what the charge is. We have to calculate that charge. So now I see iron going from 0 to +3. And so when it goes from 0 to +3, if it's becoming more positive, that means it has lost electrons. So we see that iron is losing electrons. That means oxygen must be gaining them because I have to have one losing and one gaining, and that makes sense based on what I've seen with my charge here with the oxygen, that it becomes a 2 minus, and because it's gaining 2 electrons. So it's gaining those electrons. So what I know is if something loses electrons, then I know that by definition this is considered an oxidation process. Now, we can figure out what's happening with the oxygen in one of two ways. One, we know that we have an oxidation, therefore the other one must be a reduction because they happen in pairs. But we can also look at this and say, okay, we gained electrons, we're reducing the charge, we're going from a 0, so we go from a charge of 0 to -2 for the oxygen, whereas here we went from 0 to +3 for the iron. And so therefore we know we have a reduction because what we're reducing is the charge on that particular atom. Now we want to look at some biological reactions. We got to deal with the gain and loss of oxygens or hydrogens. Now for me, gaining or losing electrons, I can get that with the oxidation and reduction, but sometimes it's a little bit more challenging to remember what we're talking about with oxygens and hydrogens and which one is oxidation and which one is reduction, because we have all this gain and loss and all these different things. So one thing that can help you is if we look at oxidation, okay, it has oxy in it, sounds like oxygen, and so this is actually the gain of oxygen. And notice anytime I have the gain of oxygen, the opposite must also be true for hydrogen, that I must be losing hydrogen. So if I can remember that oxidation is the gain of oxygen, then I can actually remember everything else about the oxidation and reduction. Because if oxidation is the gain of oxygen, the opposite is losing hydrogen, and therefore reduction must be the loss of oxygen or the gain of hydrogen, because they are opposite things happening. So just kind of a way to help you remember that once you're setting it up. And so if you're on the exam or working on a problem, it might be a good idea to kind of write out this analogy just so you can see the connections rather than trying to do it from your head, because sometimes we can get ourselves a little bit mixed up when we're trying to debate which one it is. So what I want to do is look at this particular reaction, and it tells me some information below. It says, in this reaction, NAD plus and NADH are large organic molecules whose structure is not important. That means I don't care what it looks like. All we're really worried about is this one little fact in here, is that NADH contains one more hydrogen than NAD plus. Okay? And then it gives us this LAD, that's the enzyme that helps this whole process go. But this that I boxed in here is the critical thing to understanding what's going on in the reaction. And so what I look at is if I look at my NAD plus, I say, well, I know I go from NAD here plus to NADH, and it tells me that NADH has one more electron, so I can actually put down here that we gained a hydrogen. Now I can go back to my table up here, and I see that if something gains a hydrogen, it is in fact a reduction, okay, simply from gaining that hydrogen. Now I can also look at, this is actually ethanol here, and now what I'm looking at here is how does this change? As I go from my ethanol over to my product, I see that I have the same number of carbons, I see that I have the same number of oxygens, but I have a different number of hydrogens. I'm actually losing hydrogens here, so I'm losing hydrogens. And this makes sense. If one substance is gaining hydrogen, the other must be losing hydrogens. And so we can label this as an oxidation because we've seen that we're losing hydrogens, therefore it's an oxidation. We also know that we've got an alcohol group here, so that's a carbon-oxygen single bond. Here we have a carbon-oxygen double bond. So although we don't gain oxygen, we're gaining bonds to oxygen. So it kind of further supports that this is an oxidation. And now we look at our results. We see loss of hydrogens, gain of hydrogens, 1/2 oxidation, 1/2 reduction. So this part is just going through some more examples. We're trying to figure out what's undergoing oxidation, what's undergoing reduction. And what I want to look at is say I've got to look for one of three things: gaining or losing electrons, gaining or losing hydrogens, gaining or losing oxygens. So I'm going to go through each of these and see what I can figure out. Now here in the first one, I see no oxygens or hydrogens. That tells me that that definition is not going to be of any help to me at all. I'm going to have to look for electrons. And so I look here, and just like I did with my iron, I see that these elements by themselves have a charge of 0, that sodium has a charge of +1 and chlorine has a charge of -1. So what I see happening is sodium goes from 0 to +1, and in order for it to go from 0 to +1, it must lose an electron, and when I lose an electron, that is known as oxidation. So I can put my sodium in here. And again, because I know that the sodium is being oxidized, the chlorine must be reduced, but I can also look at my charges here. Chlorine was neutral to begin with, and then it has a -1 charge in the molecule, in the compound, so it's being reduced because it's gaining an electron, but it's gaining a negative charge, so it's undergoing reduction. And so we just say Cl2. Don't worry about whether we say Cl or Cl2. What we're doing is just identifying the substance, identifying the reactant that is undergoing reduction. So just write it just as it is on the reactant side. Now we look at our burning of coal here. That should be a capital O there. Let me erase that. And so this should be CO2 there, big O there. So we have a balanced reaction. Now what I want to look at is, I'm trying to figure out what is happening here. Now for me, I'm going to look at my electrons first because I'm going to try to do it with that. So I have 0 and 0. I'm not dealing with an ionic compound, but what I can look at is I can say, well, in a compound, I'm not going to have oxygen with a charge of 0, even if it's in a compound. What I am going to do is see that the oxygen is going to gain electrons. And so even though it may not have a full -2 charge, I can still see that it's going to undergo reduction because I don't ever see oxygen losing electrons to become more positive. So I can see here that my oxygen is going to undergo reduction, and that the carbon therefore is they're going to undergo oxidation. Again, because carbon's a little bit in the middle, I know that oxygen's reduction, so carbon must be oxidation. I can also look and see that carbon here has no oxygen bonds, and on this side, on the product side, that carbon has now bonds to oxygen, so it has gained oxygen. So again, that agrees with my definition of oxidation. Once I've identified either the oxidation or reduction, then the other species must be the opposite. Now I can look down here at my metabolism of glucose. And so what we're looking at here is the formula for glucose. That's a carbohydrate. We'll be looking at those very soon. And we have oxygen. And I'm actually going to take the same approach that I took in the previous problem. I look at oxygen as an element. I know it has a charge of 0. And even though these aren't ionic compounds, we're not going to get a cation and an anion in these compounds, I know that when I start to look at how electrons are behaving, that oxygen is going to gain some electron density. It's going to be like a polar covalent. The electrons will spend more time around that oxygen than they do around the carbon. So we have a more negative species, even if it isn't a fully negative charged element. And so I see the same argument that I made before. I see that my oxygen is going to be my reduction process, okay, and that the glucose, the C6H12O6, is going to be the oxidation process. It's a little bit harder to see with the oxygens because of what's going on. I can see that here I have carbons with hydrogens attached. Here I have carbons with no hydrogen. So I've lost hydrogens, which is also one of the markers for an oxidation process. So we can apply a couple of different rules to these. It's just a matter of determining one, and then the other one must be the opposite because I must have an oxidation and a reduction. So the picture up here at the top just lets us see something about going on in the citric acid cycle. And what we're worried about here is determining whether we're dealing with oxidation or reduction. Here I've got my NAD+, which I saw earlier, going to NADH. And I know that my NAD+ is gaining a hydrogen. And when I look at my definitions of oxidation and reduction, I know that that means that my NAD+ is undergoing my reduction, which means that the malate must be undergoing oxidation. And I can also see this if I look at the structure. What I'm going to see is that I'm doing something about the number of hydrogens here. I'm losing hydrogens from this part of the molecule, and therefore I'm losing hydrogens, and that's a hallmark of an oxidation process. So the last example we're looking at here is about cataracts, and they talk about what cataracts are, which really doesn't have any bearing on this particular problem, and it's caused by protein precipitation in the lens due to high concentrations of sorbitol. It's a sugar alcohol, so it forms from glucose here going to D-sorbitol. And so what I look at when I'm looking at the molecule is, again, I'm looking at what I have present, and there's a couple of things I can look at. I can look at this part of the molecule. I see that everything else is the same, so I'm really only worried about this part. And I see that here I have a carbon with 1 hydrogen and 1 oxygen. Here I have a carbon with 1 oxygen and 3 hydrogens. And so as I go from the reactant to the product, I am gaining hydrogens by the glucose molecule. And so when I look at my NADPH, which is a little bit different than the NAD+, but again, we're not worried about what it is, just knowing that here it has a hydrogen and here it has lost that hydrogen. So from here to here, we're dealing with the loss of hydrogen. And so anytime I'm dealing with the loss of hydrogen, I know that that is going to be my oxidation process. So my NADPH will undergo oxidation, and my glucose here will undergo reduction.